Hi, this is Kutani, and this is part 2 of my Kerbal Space Program Getting to the Moon series. In this video, we will be getting from the launch pad into orbit, which should make for a fairly quick video, but I'll try to give a little bit more information before we get there. So, in our last video, I created a rocket, which you see here. I've added 2 batteries to the lander stage, which I forgot to do in the last video. It just gives us a little bit more energy to drain if we go into eclipse, and yeah, that's the only major change since the last video. So new things we're introducing: we still have our Delta V stats, which we'll be using throughout the rest of the mission. And at the bottom we have 2 custom windows that are both MechJeb windows. The only one we care about is this one on the left, which is just a shortcut information to show our apoapse, periapse, time to each, and our true altitude. The altitude indicator up at top indicates the altitude to sea level, altitude to whatever the game considers to be sea level, even if there isn't a sea on the given body that we're orbiting. So you might find, if you're only going off of these numbers, that you end up just crashing into a mountain, which is 100, 1,000, 2,000 meters above the zero level. By having the true altitude indicator that MechJeb provides, I know exactly how far above the ground we are. Mostly I use this for the apoapse and periapse data, so I'm not having to constantly switch back and forth in the map when I'm getting into orbit. So getting into orbit. Essentially, any rocket, you don't just go up to get into space. To get into orbit, you have to go sideways very, very quickly. In real Earth orbit, that velocity is roughly 8 kilometers a second that you need to be moving sideways to stay in orbit. In Kerbal, it's about 2.5-ish meters, about 2.5 kilometers a second, roughly. Depends on what altitude you're at. Now, during our ascent, what we will be doing is going straight up to about 10 kilometers, and then we'll begin our gravity turn to the east. We wait until about 10,000 because that gets us through the thickest part of the fairly soupy atmosphere that Kerbal Space Program has. We don't want to go through the atmosphere at an angle this low because we're spending too much time in the lower atmosphere. So we go straight through it. At that point, we'll start turning over to start gaining our sideways velocity. The one thing about the atmosphere, especially in the lower parts, is that the game does model terminal velocity, which means it doesn't matter how hard you're pushing, you aren't going faster than what the velocity that the atmosphere allows, without it being completely counterproductive. The way of counteracting that is to lower your throttle if you're hitting that point, but it's hard to gauge exactly where that is on the fly. And this is the only autopilot mechanism of MechJeb that I use in the ascent guidance menu, which is the limit to terminal velocity. There's also a prevent overheating one. I very rarely hit a point where I actually overheat, so I don't ever run into it, but I get very annoyed if it does happen, so I leave that on. But I do limit it to terminal velocity to maximize my delta V on ascent. Just a personal preference. Other than that, I don't really use the other features too much. So what you'll notice as we ascend, as we hit terminal velocity, especially early in the ascent, my throttle will be automatically lowered from 100% by MechJeb as we get further towards space. Other points of note. I'll be going over the maneuver node system once we are actually getting up to the point where our apoapse is at the altitude we want to set our orbit at. And I think that's it for this particular intro. We'll be paying attention largely to our delta V stats during the first part of the ascent, and that I'll use that to gauge when to stage as opposed to the fuel meters down here, because it gives me a little bit more time and I can be a little more accurate. And occasionally I do forget to stage, especially if I switch to the map view. And it's really annoying to find out you've wasted however many tens or hundreds of meters of delta V because you forgot to remove some vestigial piece of your rocket you no longer need. So we'll be using that. And I guess we can get going. So I will throttle up to 100. Jebediah looks good. He looks happy to be where he is. I press T to turn on SAS. This will keep the rocket nice and stable during the ascent so that I don't have to constantly adjust it. And we will lift off. Because we added so many engines to this, our initial ascent is actually very quick. And you'll notice that the thrust to weight ratio is actually increasing as we go. That's because we are burning mass to push us along. Nice view of the Space Center there. The moon's actually currently in a position that would be good to do a translunar injection, but we're going to get ourselves into a parking orbit first. Alright, we're coming up to our first staging point, and staged. And there they go. We won't do our next stage until after we've started our gravity turn, which will be coming in about 3,000 meters. I go ahead and turn off SAS, since I'm going to be taking manual control. You can see there's still a little tiny bit of rotation as we go up, but it's not too bad. And we're close enough, so I'm going to begin my rotation. We go east, and you'll find even in the real world, all space launches will launch to the east, because the planet rotates towards the east, which means if you launch in that direction, you pick up a free several hundred meters per second of delta V. It's not a huge amount, but it helps. And when you're dealing with very, very large and very expensive rockets, and your delta V requirements are razor thin, you get everything you can for free if you can. You can see now I'm just very slowly shifting the rocket over towards 90, and there's our stage. Very slowly bringing it towards the horizon. We are now in the upper atmosphere, which means we want to get more and more sideways. We don't want to go too much against our prograde vector, because otherwise we're just wasting fuel. Real rockets actually use, it's called a gravity turn, because real rockets use their mass and gravity to turn them as opposed to worrying about some sort of thrust vectoring, though they do use that as well. Okay, I'm going to press SAS to hold this position. Our apoapse is coming up to 70 kilometers. I'm going to cut thrust at 75 kilometers, and I will set up our maneuver node to circularize our orbit. I admit this isn't the most efficient orbit I've ever done, but it's alright. And 75. We'll now look at the map. We're about 1 minute 21 seconds away from apoapse, so I will click there, add maneuver node. I'll extend the prograde vector out, move it over, bring it back retrograde a bit, try to match our apoapse and periapse around where we want to be, around 75 kilometers. Press period on my numpad to bring up the ball here, and I will move to our node vector. Now you'll notice that it shows our estimated burn is 48 seconds, and I'm going to pause to give me time to explain this. The estimated burn is calculated based on what the game has seen from your most recent burn. It's sort of an average. If you were running at full thrust, you're going to get the estimated burn at full thrust. If you were running at half throttle, you'll get the estimated burn at half throttle. And what you want to do is you want to look at the estimated burn time, then divide it in half. And you want to put half of the burn in front of the maneuver node and half of the burn after the maneuver node. If you wait until you hit the node to start your burn, you're going to find that the resulting orbit that you get is completely off what you expected, because it took you time to get that change in velocity to accomplish that, in this case 814 meters a second of delta V. If we spread our burn over a time from before and after the maneuver node, it comes out much more even and we'll get more correct results. Since in this case it shows our estimated burn time is 48 seconds, I'm going to start my burn at T minus 24-25 seconds, which we've got a number of seconds to go before we get there. Last time I tested this, I actually managed to only require about 200 meters a second of delta V for the change, which was much more efficient. Alright, and there's our burn. Turn on SAS while we burn. Make sure it doesn't shift around. If you have an unbalanced rocket, you definitely want that on, because otherwise you'll be thrusting and you'll notice your vector is your spaceship is trying to go in all kinds of directions you don't want it to go in. RCS helps a lot with that, but we're not covering that in this video. So we are at we are at T, and we were about halfway through our burn, so we're pretty good. Switch back to map and look above, and we can see, as per our custom info window, our periapsis is rising. 4, 5, 6, 7, 73, and 81. Not perfectly circular, we could adjust it, but for our purposes now, it's pretty good. Oops. Let's kill that maneuver node, and we are now in orbit. Our remaining vacuum delta V is 928 meters a second. If you'll recall from the last video, we estimated that our launch, ascent, and orbital insertion stage gave us roughly 5,000 meters a second of delta V. Since we've ended up with 928, that means we've burned a little bit more than 4,000, which is a pretty efficient, pretty good orbital insertion. I'm pretty happy with it. Done better, but not by much. From here, we'll be going on to the moon, but that will be in another video. So, until next time.